first topic that I'm going to talk about is the ROC curve. Okay, so from the talks from before, I've told you. So we'll go ahead with the following outline. It's the definition, components, calculation. How do we interpret? What are the applications and what are the limitations? So, an ROC curve or receiver operating curve is a graphical representation used in statistics to evaluate the diagnostic performance of a binary classification model. So, this is something like a diagram which is there below, right? Is an example for a receiver operating curve. So, what do you mean by binary classification? Usually, it would say it is good or bad. Okay, one of those things, yes or no, whether the test is positive or negative. For such data or such calculations, we can use something like a receiver operating curve. Okay. So it plots the true positive rate or the sensitivity on the y-axis as compared to the false positivity rate, that is 1 minus specificity on the x-axis. So in this graph here, you can see the y-axis showing the true positive rate and the x-axis showing the false positive rate. Okay. So coming to the basics again. So what is this, graph, or this is this diagram called as? It's a matrix, correct? So the answer for this, it's called a confusion matrix. Why is it so confused? Because in statistics we are trying to arrive at a conclusion assuming one thing. We have one part on the left hand side, if you can see, we have something called as the actual class, which probably can give us the actual statistics in nature. But what we usually do is we find out the predicted class, right? Based on this, we get an assumptions of true positive, false negatives, false positive, or true negative, based on which we can calculate the type 1 or the type 2 errors. Correct? So this is what is the basic understanding for any basic statistical tool analysis. Okay. So coming to the components of the receiver operating curve, you have the true positivity rate and you have the false positivity rate. Correct? These are something that I've already mentioned. That is the x-axis and the y-axis. Okay. Next important thing is the threshold. Okay. The threshold is the model's probability cutoff to decide whether a sample belongs to the positive or a negative class. I told you earlier that it's a binary model. It will only tell us if it is positive or negative. Correct? So this threshold helps us adjust the effects to the true positivity rate and the false positivity rate. Okay. The binary classification, the threshold becomes the most pivotal component. Okay. And hence it helps us get a consideration of whether the test result is positive or negative. So here, let us take a diabetic screening test as an example. So all these horizontal lines that you are looking at, they are thresholds. They are cut at regular intervals by a vertical lines. Correct? So if you place your cursor anywhere on these points, you will get a particular threshold. So that threshold can help us understand the probability cutoff. Okay. So having said this, this usually does not help us get the probability. It will only make us assume a probability, and based on the assumption of the probability cutoff, we can tell whether it is positive or negative. Okay. That is one of the limitations of the ROC. I will repeat again. The probability cutoff is something like an assumption that we make in a receiver operating curve. For example, we have in this case, we can take the diabetes itself as an example. So if you take an FBS of 126, that becomes the probability cutoff value. So it is between 120 and 130 here, right? So that can become the cutoff value. That can be the threshold value. Okay. So it's something like that. So you can keep the threshold wherever you want. And then based on that, you can see what is the receiver operating curve mechanics like. Okay. So that is what we need to understand by the meaning of threshold. So the components are, by summary, the true positivity rate or sensitivity, the false positivity rate or 1 minus specificity, and the threshold. These are the components of a receiver operating curve. Okay. The receiver operating curve plays many important roles in medical statistics. The first being that evaluates the test performance. So it plots the sensitivity against 1 minus specificity, that is the false positive rate. It usually acts as a trade off, that is between true positives and false positives. the thing is, we want to minimize the false positives as much as possible by including the true positives as much as possible. So it is usually a trade between these things. So there is no test which will have all the positives being correct. So if that happens, it can be an ideal curve. Okay, I will show you what that means. Okay, what is an ideal curve? So unfortunately, none of the tests which are there out in statistics or anything in medical science will not give you the true positives as 100%. There will be some false positives which come off. So that is one thing we need to understand. So whenever we are calculating ROCs, false positives also gets included, and it is usually a trade-off between these two components. It usually visualizes the test performance across all possible cutoffs, that is, the values or the thresholds. The second important component of ROC that we need to understand is the diagnostic threshold selection. I told you earlier, 126 is what we took as the diagnostic threshold. So, whenever you are trying to make a diagnosis of a positive or a negative ROC, it depends on the threshold. Okay. So it usually balances the sensitivity and the specificity, and the based important thing is the clinical need of that particular study. So whatever you want to analyze, for example, diagnosis of diabetes based on fasting blood sugar. So at that particular time, what specific threshold needs to be chosen will be the optimal threshold selection for that particular diagnosis and test. Okay, there might be different thresholds depending on what we want to analyze. Okay, what importantly we need to know is, because of these thresholds, there can be missing of cases which becomes very dangerous. It probably favors sensitivity, but at the cost of specificity. Okay, false alarms are usually costly when we are thinking of more about specificity. So what usually happens, the sensitivity starts dropping down. Okay, if you see the graph in the further slides, I'll help you understand that. Okay, most of the times, equal weightage have to be given, and usually a balance needs to be struck between these two components. The third important thing in receiver operating curve is the test comparison. Usually, you need to check multiple area under the curve. Okay, probably for a test with a threshold of, say, if it is 1.2, 126, probably you can choose it between 130, 150, and then see the curves. And based on these curves, you can analyze where they fall under. Okay, the perfect test score, as we were assuming to all the true positives, will give you an area under the curve as 1. Okay, and by and large, the assumption is the random guessing will be around 50%, that is zero point 0.5, that is midline. So it helps us determine which test among the two or three, whichever number we have taken, is better or superior compared to the other. So coming to an example now, we have the x-axis with the false positive rate, we have the y-axis with the sensitivity or the true positives. So by random guessing, what will happen, it is the 50% line, that is the dotted line that you see. Correct. Anything which comes above the random effect, closer to the true positive, here usually you get true positives, that is 1. Okay, anything to the left of the random effect gives you an assumption of a good area under the curve. If anything comes after the line of random effect towards the right side, it usually gives you a poor assumption for the area under the curve. Are you guys clear until now? So let's take an example so that it becomes more clearer. So you guys know the x-axis, y-axis, and the thresholds, right? So we are taking the same example of diabetes so that there is no ambiguity in understanding. So we know what are each points representing here. So let us take an example. What will happen if we choose different thresholds? Okay, so for example, here we have chosen 126 as the optimal threshold that we want to say that the patient is diabetic, right? So if we choose 126 as the optimal threshold, what is the sensitivity we have? Sensitivity is around roughly more than 75%, and the specificity or the false positive rate is as less as 18%. So what if we reduce it? We'll reduce it to 120 or say around 110. The sensitivity here goes up, right? It becomes very close to almost 90% or 100%. But what happens to the false positivity rate? It increases as well. From 18% for 110, it is almost up to 45%. So this is something that we need to understand. This is the trade off that I was speaking about. Always remember, the change in the threshold, there will be changes in both the sensitivity as well as specificity. The thing is, which has the least amount of change, or which gives us the better curve among the outliers or the random effect towards the right side or closer to the ideal effect, is what we need to choose as the threshold. Is it clear until now? So the key observations here, as I've already mentioned here, okay, so 126, 75% is roughly the sensitivity, 18% is the false positive rate. So more or less, if we change it either side, we are going to have a trade-off between the sensitivity and the false positive rate. Okay. Similarly, I forgot to mention about the higher end. That is, if it is closer to 160. So what usually happens is the sensitivity drops here, correct? The true positives might be lost for us. So at this particular time, we are going to reduce the false positivity rate, but number of people who need to be diagnosed are something that we are actually compromising on. So this is what we need to understand. Okay. So it's usually the balance between sensitivity and specificity that we need to observe in the receiver operating curve. So by this, I think so it becomes very simple and easy to understand. So the perfect classifier is something that you have 100% true positivity rate and a zero false positivity rate. Okay, so if you have 100 positivity rate, the curve almost touches like this and it becomes an L, correct? Inverted L. So this is what is the ideal situation, but unfortunately, none of them come close to that. Anything moving closer to this would be a better ROC as compared to the opposite end. And random classifier, as I told you, gives us the 50-50 chance of the curve going either to the left or to the right. Okay. Coming to area under the curve, area under the curve measures the area under the receiver operating curve. Okay. It can range from 0 to 1. Okay. 0 is the perfect classification. Zero point 0.5, no discrimination, or it helps in random guessing. This is the zero point 0.5 random classifier. Less than zero point 0.5 usually have worse than random, or it can have an inverted prediction. Okay. Calculating the area under the curve, usually there are multiple ways that can be calculated by. Okay, there is something called as a trapezoidal rule. These usually, there are many calculators that are readily available, but this is the formula which is uses. It is a summation. Okay, summation and the average of the following components, that is the false positivity rate at a particular threshold to the true positivity rate at that same threshold, divided by the number of thresholds which are considered. Okay, so this you have to take an average after getting a product of these two things. Okay, so basically this is calculated by the system when you feed in the data. Okay, another probability another test which can be used for calculating the area under the curve is the probabilistic interpretation. What it does is also it uses a formula. Okay, and based on this it gives us a value. So all these values that were either by the earlier method or the probabilistic interpretation, it gives us the ROC curve, which gives you this thing a score between 0 to 1. Okay, so that is what we need to understand. So how do we go about the steps? Sort out the scores in descending order, compute the true positivity rate and the false positivity rate at each threshold, plot the ROC curve, use either the trapezoidal rule or the probabilistic comparison to compute the area under the curve. Okay. So why is AUC important? A single AUC curve offers a quick comparison for multiple models. Okay. If you have multiple models which are giving you the same answer, which you can come to a conclusion as which test is better off. Correct. You can see the curve and you can guess it whether it is going towards the more sensitive version, which comes to close to the true positive rate. Okay, one is that. The other important thing is in the data sets where one class is significantly dominating, especially when the metrics are not accurate, both an area and under the curve which incorporates the true positivity and the false positivity becomes more reliable metric for us to come to a conclusion. Okay, this is something that we need to know. When things are not accurately mentioned, or nothing is clear about, sometimes you see studies which they give you certain data and certain data are missing. At that particular time, if you are able to get an area under the curve for that particular test, it will give you a better visual feedback telling that okay, this metrics have been tested, and probably it is a valid test. Okay, so that is what it gives us. So again, coming to the same ROC, so the take home in this would be, you need to know, uh, it's a graph which has a thing with false positivity rate being on the x-axis and the true positivity rate being on the y-axis. Anything close to the y-axis or onto the left shift, it is a better ROC curve. That is, it is moving closer to the one value. Okay. Point 0.5 is the 50-50 line. It is called as the random classifier line. Okay. What is the applications? It helps us in clinical decision making for a particular screening test or a diagnostic test. Okay. It helps us, determine if that particular test is good for clinical use as well. It informs us whether additional testing can be needed. If it is very close to the random line, probably it might not be a very easy decision making at that point of time. It can help us understand that, okay, additional supporting would be required, or larger sample size would be required. Okay, it usually helps us make a evidence based practice as well. Okay, research applications similar to what I've already spoken to. Clinical trials and diagnostic methods can also be usually based on ROC curves. Okay, so what are the limitations? Actually spoke to you about this earlier. Okay, it does not account for the differences in the number of positive and negative cases. You just have to feed the number of cases. It takes it. That's it. But it doesn't put it. It doesn't matter if the positives are on one side, which are more, and the negatives are less on the other side. It doesn't matter. Okay. It doesn't account for those differences. It treats false positives and false negatives equally. Okay, it's simple terms. This might not be a real world scenario. It doesn't suggest an optimal threshold. That is something that I want you to understand clearly. Okay, we need to tell what is the threshold. Okay, based on that particular threshold, the ROC curve would come up. Okay, so that is something that needs to be seen. Sometimes, even if you don't set a particular threshold, randomly you can see what is the graph which is being formed based on the true positive rate and false positive rate for that particular threshold. Okay, it calculates for each particular threshold what is the true positivity rate and the false positivity rate. It focuses on ranking prediction rather than the accuracy. So that accuracy is something that is not focused on. Okay, so it only gives us an understanding about where the rank of that particular curve is. Okay, if you want to have a better curve which doesn't have the above limitations, the thing that we need to consider is a precision recall curve. In a precision recall curve, sometimes you'll be able to tell a previous data. Based on that, you'll be able to draw conclusions. Okay, so in summary, x-axis is the false positivity rate, y-axis is the true positivity rate. Lower thresholds generate more false positive rate. Higher thresholds can miss more true cases. So this is the trade-off that we need to understand about. Okay, the closer the curve is to the top left corner, the better is the model's performance. Okay, thank you. Coming to the next topic is about correlation and regression. Okay, so both correlation and regression are a comparative statistical tool. When multiple variables are present in a study, these tools help us understand what is the relationship between these two variables. It can be two variables, three variables, and so on. Okay, I'll be discussing about that in the later slides. The important thing is, whenever we take any of this, no, it depends on the data which is at hand. The type of test that we apply, where may be correlation or regression, depends on the type of data, whether it is normally distributed or not, whether it is an ordinal data or a nominal data. Based on this, a particular type of a statistical tool can be chosen. Okay, always remember, no single test is superior. In many instances, battery of tests can be applied or should be applied for us to get a better outcome. Okay, so this is something that we need to discuss with the biostatistician once we get the results out. Okay, so they will be helping us understand much better as to what is better for us to use, which type of a regression tool or which comparator tool that can be used. Okay, so when do we use regression or when do we use correlation? What does regression tell us? What does correlation tell us? Regression and correlation are easily confused, right? So correlation usually measures the strength of the association between the variables. Okay, it is usually is based on the data which is already available. Okay, it just tells us the strength of association between the variables. Okay, whereas regression helps us quantify the association. So based on whatever data is available, you make a correlation, and regression will help us quantify that association. Okay, you find an association. Okay, that might be a positive association, negative association, or reverse association. Okay, any of this. So based on this, it can help us predict the further studies. Okay, so regression is a predictive tool, whereas correlation is a tool which helps us understand the strength. Okay, coming to what is correlation. Correlation is a statistical measure used to measure the strength and direction of a linear relationship between two variables. In this, all the things which are highlighted matters. Okay, if they ask you what is correlation, this is what you need to write. So it's a statistical measure used to measure the strength and direction of a linear relationship between two variables. Okay, relationships can be linear, logistical, or it can be non-linear. Okay, so this is something that we need to understand. Correlation is usually applied for linear relationships. It is only between two variables. Okay, so that is the limitation as well. That is what you can understand by the definition itself. Usually ranges from -1 to +1, describes how the variables change together. Okay, the examples for correlation are the correlation between height and weight in children, or the socioeconomic class and the mortality. Okay, the strength of the relationship is given by the term called as correlation coefficient, or R. Okay, the letter R is usually used for the denoting correlation coefficient. What do you mean by a positive correlation? So you take two things. Like for example, let us take weight and height. Okay, so when you take weight and height as the two things in the graph, okay, like that is the x-axis and the y-axis, what does it do? If the one variable is increasing the value of another variable, and the graph is sloping up from the left to right, as you can see here. Okay, so if it is sloping up from left to right, it is called a positive correlation. Okay, on the contrary, a negative correlation is something that the slope is usually pointing downwards. Okay, from left to right, it usually points downwards. So if the slope goes downwards for these two values when they are calculated together, that is an indication for a negative correlation. Sometimes you can also find this, correct? There will be no correlation at that particular time. It will be a random assortment of dots all over. Okay, so what usually happens is this line is something for understanding that we have put. This dots which is present here is called as a scatter plot. So a scatter plot usually helps us understand what are the data which is calculated, and based on the scatter plot data, a line will be drawn, and that will help us understand the correlation. Okay, so if it is randomly placed across, there will be no correlation. If it is moving more or less towards the right side from left bottom, then usually the upward slope, positive correlation; downward slope, negative correlation. Okay, I hope it's very simple to understand that. Coming to the types of correlation. So Pearson correlation is the first important type of correlation that we need to know. It depends on the linear relationship that I have already mentioned earlier. It takes into account of continuous variables. It is a parametric test. Okay, that means to say it is normally distributed. The range is between -1 to +1. It measures the linear dependency and assumes a normal distribution, like I've already predicted. So this is how the graph usually looks at. Okay, there will be 0, +1, -1. Anything moving towards the positive end is called a positive correlation. Anything going towards the negative end is called a negative correlation. So remember, Pearson, parametric, and normal distribution. Okay, and correlation is always a linear relationship. Okay, coming to Spearman's correlation. Spearman correlation usually takes into account ranked or ordinal variables. It is non-parametric. It measures monotonic relationships, less sensitive to outliers. Okay, and does not assume a normal distribution. Okay, here the thing which we take into account is consistency of the increase or the decrease. Okay, so here again it's about the correlation itself. Okay, so the only thing that we need to know is it takes into account ranked data or ordinal data. Okay, the other important thing is we all know Spearman correlation is non-normal distributed. If it's non-normal distributed, the probability of outliers go up, right? So the outliers, if they are needed to be assumed for us to get a better result or something like an inclusive result, we need to use something called as a Kendall-Tow's correlation. Okay, it is a non-parametric test tool. It usually measures ordinal association. It is very robust to outliers, and it can use even smaller samples for diagnosis or analysis. Okay, it usually use pair rankings for us to understand the data's movement, whether it is towards the positive concordance or it is towards the negative concordance. So usually the negative concordance is usually the data is discordant. Okay, what we understand by this is, like, say, suppose a parameter A is discordant to parameter B. If the parameters go hand in hand, they are in concordance. So this is something that is usually given to us by Kendall-Tow's correlation. Okay, so important thing that you need to remember is Kendall-Tow's takes into account even smaller sample sizes. It helps us consider even major outliers. Okay, correlation strength to interpretation. So usually if it is between point zero zero to 0.19, it's very weak. As it goes up, that is more closer towards 1, it is very strong, similar to what we saw in ROC curve, right? So anything more than zero point 0.8 is usually going to give us a good correlation. So zero point 0.6 and above, they show it as a strong correlation. Zero point 0.8, very strong correlation. So this is what we need to understand. Okay, we need to understand one more important thing. So we give something called as a coefficient of correlation, right? That was the letter R. So how do we understand that? We get usually something called as coefficient of determination. So that will help us understand the correlation. Squaring of the correlation coefficient gives us the R square value. For example, let us take a post-operative systolic BP, and the duration of hospital stay in a patient is supposed to be around zero point 0.5. So what will happen to the R square? The correlation, the two components here are post-operative systolic BP and the duration of hospital stay, correct? These are the two important variables that we are looking at. The linear relation, what we are looking at is the zero point 0.5, that is the coefficient of correlation. So R square, that is the coefficient of determination, will become around 0.25, that is zero point 0.5 into zero point 0.5. So that is roughly around 25%. So what it means is 25% of increase in the duration of hospital stay can be explained by the presence of elevated systolic blood pressure. So this is how we usually have to interpret the data when it is given. Okay, most importantly, remember, correlation should be used only when it makes clinical sense. So what happened here? We took to see whether elevated systolic blood pressure in the post-operative period increased the length of hospital stay. And by this calculation, we got to know a 25% increase is going to increase the length of stay, correct? So does it make sense always is what we need to question. So let's take an example, okay? So sometimes this type of correlation can be misleading. Let us take an example for ice cream sales and drowning deaths. Okay. So what usually has been said is there was a data or a test which was conducted, and it said that there is a strong positive correlation between the two. Okay, which is usually unrelated, but they found that as a positive correlation. So how do we interpret that? They saw that the number of ice cream sales are high and the number of drowning deaths were also very high. Okay, so based on this, what does the assumption that drowning rate and ice cream sales were equal, and that is the reason, correct? So that becomes totally meaningless. What exactly usually happens? Probably it is a summer month, and because of which there will be increased temperature, and because of which people usually had ice cream, and because of which people went for swimming as well. So because of that, there would be increased death, right, or drowning. So that particular time, just to attribute to non related components as a positive correlation would be erroneous. So that is something that we need to make sure. Okay, always remember, correlation has to make sense. If it doesn't make sense, probably we have to look into what is happening in that particular study. So whenever you're choosing two variables, they have to be related. If they are not directly related, or if it gives a positive report, please make sure that it makes some clinical sense. Okay. So always remember, correlation is not always causation. Okay. So we have two types of correlation, right? We have a positive correlation, we have a negative correlation. Correct? So here let us take a example of fasting blood glucose and a HbA1c. You have patients here whose fasting blood glucose in millimoles per liter is ranging between 5 and 20. You roughly have 12 patients. Each diamond here is representative of the HbA1c values of the 12 patients. Okay, so this is something which you see there is a upward slope, right? This is a positive correlation. So this makes clinical sense, correct? So this is something that we can consider. Similarly, if you take body mass index and the activity measure, you see there is almost like a negative correlation. It looks random here. Probably you might think it is random, it is not correlated. But if you see closely, there is a negative correlation. You see a downward slope here. Okay. So this is something like a negative correlation. Probably more or less as the body mass index goes up, the activity levels are also coming down. So that gives us some clinical idea, right? So if you have some correlation like this, we can accept it, be it positive, be it negative. Okay. So, what are the important considerations and assumptions? Considerations are, always remember, correlation is not equal to causation. It's always a linear relationship. Okay. It is sensitive to outliers depending on the type of test that we use. Always remember, context and what we are using those variables matters. Use of multiple correlation types is something that is necessary. Okay. And what are the assumptions that we make in a correlation assessment? It is always linear. It has no significant outliers. If there are any, probably you need to use a Kendall-Towns test. Always continuous variables are the ones which are chosen, or the depending on the type of variables, we need to choose the particular type of a test. Okay. Usually large enough sample size gives us a better understanding. Okay. Limitations, only measures with linear relationships can be used, and it is usually influenced by extreme values, like in the previous example when we saw these two, right? So based on this, you can actually give an idea that okay, it is positive. Probably if you take on just assume if you are calculating for fasting blood glucose only up to 10. Okay. So this still would not give us a pretty good idea. Probably it looks random. So what usually happens is these two outliers will help us put a graph towards the positive side or the negative side. So this is one of the assumptions or limitations that we need to understand. Okay. So that is extreme values usually skews the outcome. Okay. That is something that we need to see. How can we come out of that limitation? Probably increase in sample size. So it is correlation is used for exploratory data analysis, preliminary relationship assessment, probably even in economic modeling. Coming to the next concept, that is the regression analysis. Regression analysis is a statistical method used to understand and quantify the relationship between the variables. We saw the strength and direction in correlation. In regression, we are seeing the quantification between the variables. Okay. In medical research, it's commonly used to predict the outcome based on various factors. It helps us understand the risk factors for diseases, to helps us analyze the effectiveness of treatments. Okay. Regression analysis, the most important thing is you have to remember two components. Okay. The two components here are a dependent variable. Okay. Dependent variable is the variable in which the outcome, what we want or what is predicted, is labeled as a dependent variable. And what usually affects this dependent variable is called as the independent variable. Okay. So I'll give an example so that you need to know. So whenever we're talking about regression, know there are two parameters. That is the dependent variable and the independent variable. Dependent variable is the outcome, what we want. Okay. So dependent is outcome, independent is the predictor, which helps us evaluate the outcome. Okay. So it helps us understand what the about what changes in the predictors affect the outcome or the dependent variable. Okay. So it particularly helps us understand if one measure can be used as a proxy for another. Okay. For example, can a bedside test be used as a proxy for a lab test? So this is what we need to understand by regression analysis. Okay. So for example, let us understand muscle strength. Okay. So how is, if the patient is well built, how does it affect? Okay, so it might be dependent on the diet of the patient, probably the gender matters, even the exercise matters. Correct. Here what we want to know is the strength. Correct. So that is the dependent variable. So what is the independent variable here, or what is the predictors which we are testing here? It is these three, that is the diet, the gender, as well as the exercise capabilities. Okay, this is what we need to understand. Hope it is clear. Okay. Coming to the types of regression, again, it is divided into linear regression for continuous outcomes, example, blood pressure, logistic regression for binary outcomes like the presence or absence of a disease, multiple regression where many predictors are used to get a outcome or a dependent variable. Okay. Cox regression is usually used for survival analysis. Okay. This is one more type of a regression analysis. Okay. Which I'll be just specifying in the next talk. Coming to what is linear regression, it usually has one independent variable used to predict the dependent variable. So only two things are being taken into account. Okay. It is usually assumed to be linear, and the best fitting line is what is usually taken for understanding or determining the regression analysis. Okay. So the same thing that we can take up. Okay. You can take the fasting blood glucose value to the HbA1c value. So when we had this same graph earlier, we didn't draw a line, right, to see the correlation. Usually correlation, there is no need to draw a line. In regression, we draw the best fitting line. Okay. So in the best fitting line, we can see here that based on this, there's a linear regression for a fasting blood glucose in these 12 patients. Okay. So based on this particular thing, there is a upward sloping line, which is called the regression line. And this helps us get an understanding that we have to draw a particular value. So for example, if you're taking 15 millimoles per liter as the diagnostic criteria that you want to, you will see what is the roughly corresponding HbA1c. So the whole thing is, can we just calculate the fasting blood glucose just by doing a HbA1c? It will help us understand, right? That is what we want to assume here. So can just the HbA1c value predict the fasting blood glucose? So by drawing that particular line, it comes to an understanding of 9.95. So on the contrary, what I want you to understand is, by this particular graph, if a patient's HbA1c comes to 9.95, the probable regression at that particular time will be 15 millimoles per liter of fasting blood glucose. So this is what we need to understand. Whether this holds true or not is something that has to be checked in multiple trials. Okay, this is what it helps us understand. Okay. This can also be done mathematically. So if you get value for one, right, multiple other things can be calculated. So how do we do that? Usually, if this is what is calculated, right, the slope helps us get the actual value. So the 4 point, this gives us a slope of around 0.45, and that 0.45 slope is 3.2 is the regression constant. Okay. So based on the regression constant and the regression coefficient, you can calculate either the blood glucose or the HbA1c. Probably what usually happens is, if you fill in the blood glucose here, you might get the HbA1c value calculated. Okay. So that is what it usually helps us understand. So in linear regression, that is a single linear regression, you have two components. If you can give a value of a single component, it usually helps us determine the other component. Okay. Regression should not be used to make predictions outside the range of the original data. So for example, this mathematical model is only given for data in this particular set of patients. Why is that? Because a slope of 0.45 is for this particular set of patients. It might be different for different group of patients. So you need to calculate the slope for that particular pool of patients. Okay. Here, any patient, if they have a fasting blood glucose less than 5 or more than 20, they cannot be used. Okay. That is one of the limitations that we need to understand in regression analysis. Okay. Hope I'm clear till here. What is multiple linear regression? the type of regression analysis that involves more than one independent variable. So here we saw only fasting blood glucose and HbA1c. What if we add into weight or any other thing along with this, or a probable other comorbidity like dyslipidemia is what matters. Okay, if you have multiple things, how do they turn out? Okay, for example, if a researcher wants to use a multilinear regression to examine the relationship between heart disease, he can take factors like weight, hours of physical activity, etc. Probably ordinal data is what you need to collect, and that will help us understand the multiple linear regression. Okay. Coming to logistic regression, this type of regression analysis is used when the dependent variable is categorical. Okay. So previously, when we mentioned, we took ordinal data for multiple linear and linear regression. So what we are using here is a categorical data. I think so. By now, you guys have to understand what is nominal and categorical ordinal data. Okay. So these things become necessary. Based on this, a logistical regression tool is used for that particular type of data. Well, I started this session itself, I told you the type of test depends on the type of data which is usually started on with. Okay, based on that, we need to particularly apply that particular test tool. So what usually happens is if we apply a wrong test to a wrong type of data, we might not get the accurate result. You will get a result, probably you'll not be able to get the correct outcome. So that is what matters. Okay, at that particular time, it will always be wiser to get a biostatistician involved so that you can get your answers double verified. Okay, so for example, for logistic regression, what you need to understand is it helps us predict the probability of developing a particular disease based on individuals age, gender, lifestyle, and other factors. So these are something which we can categorize, right? Like for example, age of 10 to 20, 20 to 30, 30 to 40, in categorical like males, females, and transgenders. Lifestyle with again you can choose for probably activity of daily living or some other thing. So in this, we can categorize these group of patients and data sets. So if you're using this type of data which is present, then you need to use a logistical regression. Okay, so in the most important thing in logistical regression is you have a steepest change probability. Roughly in this particular say, you have only two things that can happen, that can be whether the disease will happen or the disease will not happen. Okay, so this black dot or black curve, which is the sinusoidal curve which is present here, usually gives us the logistical regression. So what we usually do is, based on the type of data, that is the categorical data we arrive at, we usually have to put the patients either in the one group or the zero group. Okay, zero would be roughly anyone below the probability of zero point 0.5. Okay, so anything below probability of zero point 0.5 will be no disease. Anyone above the probability of zero point 0.5 will be with some disease. Okay, so this is something that they plot against, and then based on this, we get a logistic curve. Okay, so what is non-linear regression? The type of regression analysis which is used when the relationship between the dependent variable and the independent variable is not usually linear, which is very straightforward, right? So what usually it says that you take an example for a bacterial culture growth over time. It is exponential, right? It doesn't go in a linear fashion. It is probably geometric progression that happens, right? So this particular type, we cannot use a linear regression tool. Okay, so for such type of data collection, the best type of tool that we can use is a non-linear regression tool. Okay, so coming to understanding these in a nutshell, okay, the types of regression that we need to remember: linear, multilinear, single linear, logistical regression, or proportional hazard regression, or Cox regression. Okay, Cox, I'll just mention it in the next talk. So always remember the dependent variable, independent variable. Whenever a question about regression is asked, please mention dependent or the outcome variable, or the predictor variable or the independent variable. These two things are something that we need to consider. So the type of test that is applied depends on the type of data, whether it is nominal, ordinal. Okay, so whether it is normally distributed, non-normally distributed, etc. Okay, so have you understood regression or correlation? Okay, in a nutshell, correlation means the strength, regression quantifies the association. Regression should only be used if one of the variables which is thought to is usually preceding the cause. Okay, so what are the differences? By definition, correlation is strength and direction. Okay, it usually gives a linear relationship between only two variables. In regression, it can be one or more variables. Okay, it can be two, three, or multiple. Okay, so usually predictor type of a tool is regression. Correlation is something like a thing which usually gives us an answer when the data is already out. Okay, so it helps us understand the relationship between the two variables. If it is positive relation or negative correlation is what correlation guides us to. Regression helps us predict, okay, for the latest studies as well. Direction, it can either be positive or negative in correlation. In regression, it can help us understand the cause and effect relationship. What usually happens in correlation is it might not give us causation, right? I already told you they can mislead us. So the causation, if at all we need to do, we can use a regression analysis. Okay, and the variables involved usually can be only two variables in correlation, and they are equally treated. It doesn't weigh in between positive or negative. It doesn't give an extra weightage for being positive and then lesser weightage for being negative. Both are treated equally in correlation. But in regression, based on the cutoff, like in logistics, I've told you zero point 0.5, something like that, right? So one variable is usually very clearly distinct as compared to the independent variables. So you have one which is fixed, that is the outcome variable. For this variable, you see how the other independent variables act on. Okay. So mathematical models usually for correlation it's quite simple. It is between -1 to +1. For regression, we already mentioned. Remember the HbA1c fasting blood glucose, okay, correlation coefficient and constant. If you remember that, that is necessary. Examples, there are multiple. You can remember one of those which I've already mentioned, like fasting blood glucose, or for example, in this particular case, in correlation, another example you can take is the number of cigarettes smoked per day and the lung capacity. Okay, these are something that you can see. It can show a negative correlation, correct? So the lung capacity decreases with the increase in number of cigarette smokes per day. Similarly, in regression, lung cancer to the number of cigarette smoking. That is what we are looking at. It's a predictive that is showing causation here, correct? So that is something that it helps us understand. Okay, so this is in just about correlation and regression. I know it's quite long and boring sometimes, but these are questions that can come. Okay, these are all simple things. Please go and read again and again. It's simple to understand. You need to revise it. It's quite volatile. Okay, so if you keep revising this, probably it'll help you, understand much better. Coming to the next talk, that is survival analysis. Is my slide visible? Okay.
Yes, sir, it is visible. Yeah.
Okay, thank you, Bona. Uh, Coming to the core concept of survival analysis. So, most of you are asking about Kaplan Meier curve, right? So, this is something that most of the times the questions have come across as well in the past. Okay. So, it's better to understand what is survival analysis. Survival analysis is a branch of statistics which is specifically designed to analyze what happens to the time and the event. What is the relationship between the time and event, okay, when it occurs. Okay, so in medical research this often means the time until death, time until the disease recurrence, duration of the patient survival after diagnosis, or time to treatment failure. Okay, usually this is what survival analysis means. Okay, it is usually designed to understand time until an event occurs. Okay, so that can be whatever, based on the aim of that particular study. So, what are the tools and techniques that are available for us to come to a conclusion of survival analysis? It can be a Kaplan-Meier curve, it can be a log rank test, or it can be a Cox regression, as I've already mentioned earlier. Okay, I'll be talking to you about Kaplan-Meier curve in detail. Okay, so what is the basics of Kaplan-Meier curve? It is an estimator used to understand survival function. So if they ask you a question about Kaplan-Meier curve, tell first thing the definition. It is a tool for survival function or a survival analysis tool. Okay. It is a visual representation which helps us understand the life table. Okay. Whatever you see, right, the step graph, that is called as the life table. Okay, the time is plotted in the x-axis and the survival rate is plotted on the y-axis. It shows what is the probability of an event. For example, take relapse for carcinoma or survival as one of the endpoints, or what is the thing that you want to study at a particular certain time interval. Okay, that is what usually is plotted in a Kaplan-Meier curve. So in the x-axis you have time, in the y-axis you have a probability. And this, what usually happens is, uh, you see over particular time, this here it will be 100%. Okay, as time progresses, depending on the number of patients studied, then you will see the number of steps. It can come down or it can remain like this and then drop. Okay, so this is something depending on the number of patients and the time in which the event has happened, that can help you understand. So this is what is the basic outline of a Kaplan-Meier curve. Okay, coming to the next thing. Okay, when you have a Kaplan-Meier curve given in most of the analysis that you have, usually it can be a one glance, and you can tell what is the result by checking the Kaplan-Meier curve. Okay, so the shape of the Kaplan-Meier curve already gives you a lot of information. A steeper slope indicates a higher event rate. The event can be death, relapse, etc. Okay, sometimes it can be the worst indicator, like when if it is a case of death, right? If it is a flatter slope, it indicates a lower event rate. That means to say the probability of survival is better. Okay, so this will help you understand. Okay, here you have a survival probability and time, right? So if there is a a steep slope which is dipping here itself, that means to say the event rate is very high. You can see multiple events happening, and there is a sudden dip which indicates decreased survival. Whereas if you see here, the slope is more flatter, right? Mostly what usually happens is the horizontal line represents the time of survival. Okay, so more the horizontal it is and lesser the dips they are, it indicates a lesser event rate and increased possibility of survival. Okay, what is survival at a specific time point? So the next thing is about time points. Okay, in that graph of time versus survival probability, you need to understand the location of time at that particular instant. What is the survival probability, right? Usually you can drop an axis for a point on the horizontal axis, as well as the vertical line is usually drawn there, and for that particular time you can tell what is the probability. For example, at the time period of around, say, suppose 12 months, what is the survival probability? It is around 85%. Okay, you need to just drop in a vertical line. Okay, the vertical line will help you understand where it stands at that particular time, and for that instance, the survival probability is 85%. Okay, so on. If you want to see for around 18 months, draw another vertical line here. Okay, whatever it touches, probably this, so roughly it has dropped to, say, around 80%. Okay, so that is how we need to check it. Okay, so what is survival duration and censoring? This is something that we need to understand more in detail. The length of the horizontal line along the x-axis of the serial time represents the survival duration. Okay, it expresses the survival duration for that particular interval. For example, so you saw this graph here, right? So you see this particular line, it is a long horizontal line. This is the survival duration for this particular interval, that is between 6 months and 12 months. Okay, so that is what I want to understand. The importance of survival time duration helps us understanding at which particular interval an event happened, an event like relapse, death, etc., depending on the study. Okay, for example, in our case, we'll take as a relapse. Okay, next important thing is censoring. What do you mean by censoring? If a patient leaves the study, or if the patient just drops out at that particular time, then the patient is supposed to be censored. That means to say we have not lost it, we have included the patient, but that data at that particular time would be censored. Okay, so that is what you need to understand. I'll be talking about specific type of censoring in the further slides. Okay, but if the patient uh, goes on till the end, probably we'll have to put a tick mark. Okay, so what usually happens is, in this particular time, we had four patients in which one patient left the this thing study. So that particular time, we need to censor that patient and continue with the study. We are not terminating the study because a patient left. Okay, at that particular time, we just put in a vertical line which indicates censoring. Okay, but what you need to understand is, if the patient left at that particular time interval, we do not end the terminal there. Okay, we do not end the interval. I'm sorry. Okay, the interval still continues. The interval will happen only at that particular timeline. Okay, So only event would be marked. The event is censored, okay, at that particular time. Hope I'm clear. Okay. So what usually happens is longer survival duration, like we have seen in the previous line, you see that the line becomes lengthier. Okay. But if the event happens quite frequently, then the uh, uh, survival duration becomes shorter. Okay. So events keep happening, right? In this case, recurrence. So up till a period of 12 months, the events were not much. That's the reason the survival duration was longer. But after 12 months, what happened? The event occurrence was increased. So you see many steps happening from here, right? So this is what usually attributes to shorter survival duration because of the occurrence of a particular event. Always remember in a Kaplan-Meier curve, right? The important thing is we just draw the horizontal lines. The vertical lines are just added for aesthetic purposes. Okay. So coming to this example here, we'll take a first year survival probability. Okay, for any case for that matter, probably you take a relapse of a cancer. Okay, so what will usually happen in the first year at the end of 12 months? You see the survival probability dropped by 15%, roughly between 75 to 100. So we are taking it as 85 here. Okay, so it was just around 85% survival at the end of first year. Similarly, what happens in the second year at the end of 24 months, it further dropped to roughly around 45%. Okay, I mean less than 50%. Okay, so totally 60% was lost. So, what usually the conclusion is, so the probability of surviving for more than 2 years is roughly around 40%. I'll come again. Okay, first year it dropped to 15%. Okay, that will be roughly 85% here. At the end of second year, the survival probability is marked around 45% here. Okay, roughly 45%. So addition of 45 to 15 will give you a 60. So drop minus 60 from 100 will be 40. So this particular thing from here to here is 40%. So at the end of 2 years, the survival probability is around 40%. Okay. Comparing different groups. Okay, multiple curves representing different groups to compare the shapes and patterns can be plotted. If the curves are parallel to each other, it suggests that there is similar survival in the two groups. So you can take cancer relapse in patients like gender wise. You can take male versus female for a particular type of cancer, or you can take smoking and lung cancer, that as well. And multiple things, if you want to suggest that there is something which is similar to both of them and the survival rates are also similar, then you can draw two Kaplan-Meier curves and then compare. If they are running more or less similar to each other, then the survival rates are similar. If they are divergent, then there will be some amount of difference between the two groups. So in this case, you can see the pink and the blue line are more or less together. That is suggesting a parallel movement. Okay, so the survival rates are similar in these two groups. Whereas in this, if you take the pink line, usually has a better survival compared to the blue line at the end of 24 months. So how do we know that? So at the end of 24 months, the survival probability is only around 25% for the blue line as compared to the pink line. Okay, at the end of 24 months, the survival probability is roughly around 50%. Okay, so this is what we need to understand. If there is a difference between the two groups here, based on that particular timeline, then we will know what is the survival probability. Okay. What is median survival? Okay, so till now we were talking about as the whole group. So what can we do about this is something that we quite often see, right? Median survival of a particular type of CA or a particular type of surgery, etc. So median survival is the time expressed in months or years when half of the patients are expected to be alive. Okay, you're taking a group of say 100. If 50% are there alive at that particular time interval, that is called as the median survival. Okay, so what do we look at? It is looking at the chance of surviving beyond the time of 50%. It can be useful summary, especially in approximation analysis. Okay, so median analysis can be read from Kaplan-Meier curve at the 50% mark. Okay, so here if you're taking a 50% mark, this roughly corresponds to an age interval, but a time interval between 18 to 24 months. So 50% survival probability usually occurs at probably 21 months. Okay, that is between 18 and 24 months. So that is what is meaning of median survival. Okay, so 50% survival probability, what it corresponds to in the timeline, gives us the median time of survival. Okay, hope I'm clear till here. So, for understanding purposes, what is the median time of survival for a true patient treatment? So, say supposedly you had two drugs which are being treated given for a treatment for any particular type of illness, say reducing blood pressure. So, if you want to see what is the median time of survival between treatment A or treatment B, you can see here there is a significant p-value that is less than 0.001. If you see the median time of survival, that is 50%. For treatment B, it roughly is between 24 to 36. For the treatment, the treatment A, it is between 24 to 36, and treatment B, it is between 36 to 48. Roughly, it's more closer to 48, right? So what usually it says is treatment B seems to be doing better than treatment A in survival analysis. So more than 50% of the patients in B treatment survived beyond the 50% mark as compared to a treatment group of A. That is what we understand by median time to survival. Hope I'm clear. Coming to the next important thing that I've already been mentioning earlier, censoring. What happens if one of the patient leaves or dies, okay, in between? So these particular things are noted as events, and these events are something which will be marked by a vertical line called as censoring. Okay, censoring is a critical concept in Kaplan-Meier survival analysis, which accounts for incomplete follow-up data in survival studies. The type of censoring can be right censoring, left censoring, or interval censoring. Right censoring usually happens when event of interest, for example, death, disease recurrence, has not yet occurred by the end of the study, and before that, the participant is lost for follow-up. Okay, you have a particular thing in mind. Okay, the thing of interest event was death, but what happens? The patient leaves in between that itself. So if that participant is lost, then the patient that particular type of censoring is called right censoring. Example, patient drops out of the study before the event occurs. The study ends and the participant has not experienced the event at that particular time. Even that can be censoring as well. Okay. So post that event also the participant is alive. Many times it happens, right? So that is also called as right censoring. What is the implication? The data is used up, usually to say that beyond that particular time of survival that we looked at, the patient is still alive, right? So if the number of right censoring goes up, probably Kaplan-Meier analysis will help us analyze that particular data better. What is left censoring? It occurs when the event of interest has already occurred before the participant enters the study. Okay, example: a patient joins the study on disease survival. Okay, but the patient was already diagnosed with that. Okay, so that particular thing becomes firstly biased, and that particular thing has to be censored. So this is something called as left censoring. Can we take this patient? Yes, probably we'll get to know this in between the study, right? So at that particular time we might have to censor it, and that type of censoring is called as left censoring, often handled differently because Kaplan-Meier curves usually don't take into account of left censoring. Okay. Coming to interval censoring. Interval censoring happens when the exact time of event is unknown, but it is known to have occurred in a specific time interval. Exact time is not known, but it will happen between a time interval. Okay. Yes, example is a participant misses a scheduled follow-up visit, and the event is discovered when he comes for the next routine visit. Say, suppose you have to mark it between 6 to 12 months, but the patient was supposed to come at 6th month, he doesn't come up. Okay, but then he comes at 18th month. So at that particular time, there'll be an event interval censoring for the previous two missed intervals. Okay, so this is called as interval censoring. So this requires many other type of survival analysis. Okay, Kaplan-Meier does not take into consideration both left censoring and interval censoring. Okay, so this is something that can be handled by a log test or a Cox proportional hazard or the Cox regression model. Okay, coming to the practical snippets, what you need to remember about uh, Kaplan-Meier curve, it is important to check what is the shape of the curve. Okay, so curves that have many small steps usually have a higher number of participating patients. whereas the curves with larger steps usually have a limited number, probably the sample size is less. Okay, what we need to understand is smaller the sample size, lesser the accuracy. Okay, about sensor data, we need to understand one thing: distribution and censoring have to be maintained. It gives us, if a particular study has a lot of censored patients, probably the study is less accurate, or people are leaving in between the study because they are not finding adequate results. So we need to think about that particular study. Okay, so most importantly, in clinical medicine, when we see a lot of censoring happening for a particular period of time, either the patient would have been lost because of death, or they've not been seeing effective results for that particular treatment. So if you see a lot of censoring happening in a particular interval, these are the questions that you need to ask as to why the censoring happens. If the result analysis or the discussion in the paper is mentioned as to why that many incidences of censoring happen, then it is good. If it is not there, probably you need to question twice about the accuracy of that particular analysis. Okay. Also remember, if there are no sensor data, probably it is too good to be true. So that is also something that we need to keep in mind. Okay. So Kaplan-Meier curves are great to visualize the difference between two groups. It helps us quantify the differences. Okay, and if at all you want to do more than two groups, probably you need to check a chi-square test and then do a log rank test. Okay, along with that, you can also use other statistical tools like the Cox proportional hazards. So two things we can use a Kaplan-Meier curve. More than two things, you need to do a log rank test. What is a log rank test? It is another type of a statistical tool which helps us understand survival analysis. It determines the difference between groups which are statistically significant. So you need to have a set of data which has been already analyzed, and you have a statistically significant data, that is p-value less than 0.05. Okay, it helps us understanding if that particular treatment intervention has some meaningful impact. Okay, it helps us cover draw up survival curves, and it just not focuses on the endpoint. So firstly, when you're talking about a log rank test, you need to have a study, you need to have a significant p-value. Okay, so question it if it is statistically significant or not. If it is significant, then probably based on that you can accept the null hypothesis or reject the null hypothesis, and based on that you can probably draw a log rank test. So based on this, you can see the survival analysis, as I've already mentioned. If it is running in parallel, that is to say there is no difference in between the groups. If it is running like this, there is a significant difference, then you can draw adequate survival analysis similar to what we see in a Kaplan-Meier curve. Okay, so log rank, first and foremost, you need to have a significant data. Okay, based on that, you apply the null hypothesis. Based on that, you need to draw a Kaplan-Meier survival chart, and then you can compare the results. What is Cox proportional hazards module? It is the most advanced survival analysis technique, allows multiple variables to be analyzed at a single time. Here we saw one or two things being measured, right? But Cox, what it usually does is it allows multiple variables, and it calculates the hazard ratio for each of them. Okay, it can also adjust for confounding factors. So this is the thing which is important to understand. Okay, based on these variables, it helps us predict the event occurring based on these predictors. Okay, so it helps us understand how different variables influence the survival in the long run. For example, a simple understanding we can take is, uh, if at all we have, what is the effect of survival depending on the drugs and the age. Okay, so if you are taking these two as the independent variables, what is its effect on the survival rate if you ask, predicted using a Cox regression module. This Cox regression actually involves a lot of statistical formulae which has to be analyzed depending on the type of drug involved, when was it given, okay, what is the age group of the patient, whether the patient had pre-existing diseases. All of that can be filled into the statistical data software. Multiple softwares are there like your SPSS, etc. They will help us get a Cox regression module, and that will help us understand the survival analysis in the long run. Okay, so these are the various types of survival analysis. Thank you.